In this video, we're going to cover section 1.2 on reaction rates. Let's consider the following generic chemical reaction, where we have a series of reactants being transformed into a series of products. Now you'll recall that the uppercase letters indicate a chemical species, and the lowercase letters represent the stoichiometric coefficient for the species in the balanced reaction. The species on the left-hand side of the arrow are referred to as the reactants, and the species on the right-hand side of the arrow are considered the products. Now, one of the most important things we must remember in chemical kinetics is that reaction rates can only be determined from experiments. And the raw data needed to determine the rate of a reaction are the concentrations of reactants and products at a series of times after the reaction has been initiated. So the number of moles of a species during any point of the reaction can be given by this expression, where we have N subscript I representing the number of moles of a species I at any given time during the reaction. That is equal to N subscript I superscript naught, the number of moles of species I present before the initiation of the reaction, plus the stoichiometric number of the species I, and xi, which is the extent or advancement of the reaction. Now, as we know, reactants will be consumed and products will be formed during the reaction. To ensure this, the stoichiometric number is set equal to -1 times the stoichiometric coefficient for reactants and is set equal to the stoichiometric coefficient for products. Now, the time evolution of the reactant and product concentrations is quantified by differentiating both sides with respect to time. As you see now, we introduce a derivative for that change in the number of moles for a particular species with time. And we equate that to the stoichiometric coefficient multiplied by this change in the progress or advancement of the reaction over time. So the rate of the reaction rate, is defined as the change in the advancement of the reaction with time. That's shown here. Therefore, the rate of the reaction with respect to the change in the number of moles of a given species with time is given by this expression. As an example of how the rate of reaction is defined relative to the change in moles of reactants or products with time, let's consider the following reaction, where we have 4 moles of nitrogen dioxide reacting with a single mole of oxygen to give us 2 moles of dinitrogen pentoxide. And as shown, the rate of the reaction can be expressed with respect to any of the species in our balanced equation. So it can be equated to the rate of change with respect to NO2, O2, and N2O5. Notice the sign convention of the coefficient with respect to the reactants and products. We use a negative sign for reactants, so there's a negative 1/4 and a negative 1/1, or 1, not shown. And we use a positive sign, or it's implied here, for products. However, we must always remember that the rates are always positive quantities, that you'll never have a negative rate. The sign only denotes whether or not something is being consumed or formed during the course of a reaction. Also notice that the rate of reaction can be defined with respect to both reactants and products. For example, the rate of consumption of NO2 will be 4 times greater than that of O2. Although the rates of consumption are different, the reaction rate defined with respect to either species will be the same. Now you'll recall from section 1.1 this figure where we show the decay of a reactant and the concomitant growth of the product. And as you can see, the rates are virtually opposites of one another at any one particular point in time. So again, the rates are positive quantities. The sign indicates whether something is being consumed or formed. Now in our present definition, we've expressed the rate of a reaction as an extensive property. Extensive properties, such as mass and volume, they depend on the amount of matter being measured, whereas intensive properties, density and color, do not depend on the amount of substance present. So we've shown the rate as being equal to 1 over that stoichiometric coefficient multiplied by the derivative of the change in the number of moles with time. Now we can make the extensive property as shown here. The reaction rate can be made intensive by dividing this expression, this equation, by the volume of the system. As a result, the intensive rate of a reaction given by epsilon is dependent upon the number of moles of a species I per unit volume, which is the molarity of the species, the concentration of the species. So this now defines the rate of the reaction at constant volume. And this is how we normally will express the rate of a reaction. We'll express it in terms of that change in concentration of either a reactant or a product with time. So if you have any questions about reaction rates, by all means send me an email and we can discuss it further by email or through a Zoom appointment. Thank you.